Okay, so this is the problem I was doing today. So I'm going to go through it. It's basically a statics problem again, but the thing I used to solve this was a little different to what you normally do with just resolving forces and stuff. And it actually got me the answer in a far easier manner. So that's what I'm going to be going through. The problem is basically a right angle triangle frame over here, and threaded onto the frame are these beads which are connected by this inextensible string over here. And the beads basically have a mass, so M2 is going to be, the mass of this bead over here is basically 3 times the mass of this bead over here. And the question is quite simple. It basically asks you what alpha is when this entire system is in equilibrium. So yeah, you can imagine, because this bead has a higher mass than this bead over here, the string and the beads are going to end up slanting downwards. And the question wants you to find out what alpha is when the whole thing's in equilibrium. So if you want to give it a go, pause the video and try it out. And when you're done, I'll solve the problem and show you how I did it. So yeah, for this problem, I didn't do the normal thing that you would do when you basically resolve forces and stuff. That does work with this. I've tried it out. It actually it gets the answer, but it does it in a sort of roundabout way, and you need to eliminate loads of unknown forces and stuff. Instead, the method I'm going to be using for this, which I kind of dig for this problem, is I'm going to be using a potential energy method. So one way you can define the equilibrium condition of a system is that the net force on all of the objects inside the system is basically 0, right? Now, force, as we know, is basically also equal to, you may have seen this other alternative form of force, which is, it's basically the negative gradient of the potential energy. This is only for one dimension. If you were doing it in higher dimensions, it would be turning into a gradient operator. And a rough idea of why this is the case is because you might also know that the work done on an object is equal to its force times the distance moved in the direction of the force. Therefore, if you're inside a gravitational field, therefore the potential energy that you're basically gaining as you move the object through the gravitational field is going to be equal to the negative work done, which is basically F, which is the force, times the distance moved in the direction of the force, which is dx. So that's just sort of a rough hand-wavy reason why this is the equation as well. So if you have the net force equaling 0 when you're in equilibrium, then you can also write that du over dx is equal to 0, right? So another way you can define the equilibrium of a system is to basically say the equilibrium is when the system has a 0 gradient of the potential energy. So that means any first order nudges of the system basically yield 0 change in the potential energy. What I mean by that is, because this is the first derivative, if you vary the potential energy with respect to the position by first order, you're basically going to be getting 0. So this is the method I basically use to get this problem. And the way I'm going to be doing this is to find the potential energy of both of the masses and then calculate what du is and set that equal to 0. And by doing this, I'm basically finding out what the equilibrium conditions have to be. And in order to do that, you just need to work through the geometry of this problem in a bit more detail. So that's what I'm going to do. So if you're looking at what the change du is, you need to pick a reference point in your system to set the potential energy as 0. In this case, I found that this point over here was pretty convenient to do that. So if I set this point as 0 potential energy, that means any points below it basically has a negative potential energy because they're getting closer to the surface of the Earth, which means that they're basically losing potential energy. So that's how I define the potential energies in this system. It's totally arbitrary where you pick this reference point as 0. I could have picked it over here, but I just found out that it actually works easier for the geometry to pick it over here because I got this nice right angle triangle to work with. And what else do we know about this? Well, I know that because the string is inextensible, it's not going to change length during the process, which means that I can call it L, and that actually provides a constraint so I can figure out what alpha is. So based on this, I can basically say that this length over here, if you look at this right angle triangle, it's just going to be L cos alpha. And similarly, this length over here is going to be equal to L sine alpha. So now I know that this is L cos alpha and this is L sine alpha. I'm one step closer to figuring out what the vertical height below this zero potential energy reference point is for this mass and this mass over here. And in order to figure out this vertical height, you've got to actually use this larger right angle triangle here. So if this is 60 degrees over here, then it's an equal 60 degrees over here as well. Same thing goes for this side, which is 30 degrees elevation. So it's going to be lowering from the horizontal of 30 degrees as well. So now I can figure out what H2 is, and I'm going to call this H1. I can figure out what H1 and H2 are in terms of this L cos alpha, L sine alpha, and this big triangle here. So let me write down what those are. So H1 is going to be basically equal to L cos alpha is going to be equal to L cos alpha sine 30. So L cos alpha sine 30. And H2 is going to be equal to L sine alpha sine 60. So H2 is going to be equal to L sine alpha sine 60. And why am I figuring out what these heights are? Well, I want to figure these heights out so I can figure out what the potential energy of both of the masses are. And the reason I want to figure out the potential energy of both of the masses is because if I add up those potential energies, I get the entire potential energy of the system. And I can use calculus to figure out what du is. And once I've done that, I can set it equal to 0 to figure out what the equilibrium angle is going to be. So let's start doing that. So what's the potential energy of mass 1 going to be? I'm going to call the potential energy of mass 1 U1, and its potential energy is basically going to be equal to minus M1 because it's actually below the zero potential energy point, times g, which is the acceleration due to gravity, times this H1 term here. So L cos alpha sine 30. And similarly, U2 is going to be equal to minus M2g H2, which is going to be equal to L sine alpha sine 60. So the total potential energy of the system is going to be equal to U1 plus U2. So U, I'm going to just call it U for the whole potential energy, is going to be equal to minus, in brackets, M1g L cos alpha sine 30 plus M2g L sine alpha sine 60. Now I've got the total potential energy of the system, I can start figuring out what du is. So when you do this, basically what you need to do is, so when you figure out what du is, which is a tiny change in the potential energy, it's actually a differential change, so it's going to be really, really tiny in the limit that this becomes 0. You want to look at this and basically go, well, which of these variables over here is going to vary if you change the potential energy a little? So changing the potential energy of the system by a tiny infinitesimal amount is going to correspond to nudging these masses a little, right? And essentially the thing that's going to change is going to be this angle. This angle is going to vary infinitesimally. So in order to figure out what the potential energy differential is, we need to vary the potential energy with respect to the angle alpha, which is good because that's what we're trying to figure out. So this is going to be equal to minus M1g L. Now, because I'm varying alpha, I need to differentiate cos alpha. So I'm basically going to get minus sine alpha sine 30 times d alpha. Similarly, I want to do the same thing for this, and I'm going to get M2g L, and then differentiating sine alpha, I get cos alpha sine 60 d alpha again. So just to reiterate, the reason I'm doing this is because you can basically figure out what du is. Du is going to be equal to du over d alpha, that is the derivative of the potential energy with respect to the alpha times d alpha. So that's what I'm doing. Every time I'm figuring out one of these terms, I'm first of all differentiating it with respect to alpha, and I'm multiplying it by d alpha over here. And this whole thing, we know based on what we figured out about the equilibrium condition, we know that du has got to be equal to 0. That means I can basically set this entire expression over here equal to 0. So if I do that, well, first of all, mentally we can forget about this negative sign over here. We can check that over to this side, and that's going to turn into 0. And anything else that's common in this entire expression can get thrown over. So what we're left with is we're basically left with m1 minus m1 sine alpha sine 30 plus m2 cos alpha sine 60 equals 0. So the g's and the l's and the d alphas, because those aren't going to be equal to 0, I basically threw them over to the other side and multiplied them with 0 to basically get nothing. So I'm just left with this. So now, if we figured out what sine 30 and sine 60 is, we can end up getting closer to the answer and figure out what alpha is. So let's just do a bit of rearranging as well. Now we're going to get m1 sine alpha sine 30 equals m2 cos alpha sine 60. So now if we want to get what alpha is, we just take the cos alpha over to this side and we get tan alpha. And we can take all of this extra stuff and take it to that side. So we basically end up getting m2 over m1 times sine 60 over sine 30. Now, what is sine 60 divided by sine 30? Well, we can do that pretty easily. Sine 60 divided by sine 30 is going to be equal to root 3. So this is going to be equal to root 3 times m2 over m1. And we're told in the question that the ratio between the two masses is that m2 is 3 times the mass of m1. So m2 over m1 is going to be 3, so 3 times root 3. Therefore, alpha is basically going to be equal to tan inverse of 3 root 3, which is roughly, if you put it into your calculator, you get 79.1 degrees, which is basically the answer they got. And at this point, you can now you got what alpha is, you can start labeling the actual forces, such as the weight of this mass and the weight of this mass, and you can even figure out what the tension in the string is. But I'll leave that to you guys because it's a simple deal of just balancing the tension forces and the weights. So yeah, thanks for watching, and don't forget to like and subscribe.